In step 3, we train the prediction model. Now in step 4, we are going to run the prediction model. So after the prediction model has been trained, the tool is rerun using the projected explanatory variables to create a prediction output. That's run model. In this step, you will rerun the model using the projected bioclimate variables from the SSP3 7.0 climate scenarios for 2055. The prediction output will model maize suitability for the mid-century period of 2041 to 2070. In the prediction options section, for output prediction features, delete baseline maize suitability and type future maize suitability. Okay, we have already closed our geoprocessing pane, but no problem. Come here, it's quite easy, and just reset panes for geoprocessing. Okay. Okay, so since I restarted my computer, I'll have to fill in these variables again. So let's go ahead. It said in the prediction section for output prediction features, delete baseline maize suitability and type future maize suitability. So we are going to it said section for output prediction features. No, we can't continue from here. I'll just return back to the previous section and fill out the variables so that we can continue from there. That will be better. Okay, so this was where we stopped at the last section. So here we're going to change this baseline maize suitability to future maize suitability. Okay, and then you update the prediction explanatory variables to use the 2055 bioclimate projection variables. For March explanatory variables under prediction, click the down arrow for baseline bioclimate 01. Scroll down the list of variables to find and select bioclimate projections 01 2025. So let's see what they mean here. Oh, what they say says for March explanatory variable. Okay, March explanatory. Oh, where is it? Where is it? Variables under prediction. Under prediction, okay. Click the down arrow for baseline bioclimate 01. Scroll down the list of variables to find and select bioclimate projections 01. Okay. Bioclimate projections. Bioclimate projections 01 underscore 2055. Oh, sorry. Bioclimate projections 01 underscore 2055. That's this one. You complete this step for all 19 variables to match the prediction variables with the baseline variables that you use to train the prediction model. Under prediction, click the down arrow for baseline bioclimate 02 and select bioclimate projections 02. Okay, so we'll continue that. Baseline bioclimate projections. So you're going to see it bioclimate projections. So in a similar fashion, change the prediction variables for the remaining bioclimate projection variables for 2055. So keep doing that. Okay, baseline bioclimate to bioclimate projections 3. Okay, so go bioclimate projections 4, bioclimate projections 5, bioclimate projection 6, then bioclimate projections 7, bioclimate projections 8, bioclimate projections 9, and bioclimate projections 10, bioclimate projections 11, bioclimate projections 12, bioclimate projections 13, bioclimate projections 14, bioclimate projections 15, bioclimate projections 16, bioclimate projections 17, bioclimate projections 18, then bioclimate projections 19. 19, 18, 17, 6, 17, 19. No. Remove this. Remove this. Okay. So we have 19 here already. Let me expand this a little so that it will be clearer. 19, 18, 17, 16, 15, 14, 13. Okay. Oh, let me check the screenshot here. 1 minute. Okay. All the variables for 2055 that you will use to predict fusion maize stability and match with the baseline bioclimate variables that we are used to train the model. You are ready to run the tool. Running the model typically takes about 7 minutes but can take up to 20 minutes depending on your computer's processing power. If you decide not to train the model in the previous step and will not run the prediction model in this step, follow these instructions to add the results to your map. Okay, I'm going to add it, so let me leave these instructions, but let me just read it. In the catalog pane, expand databases, expand results.gdb, predict spatial pattern changes. How can I print? Okay, right click feature maize suitability underscore raster and choose add to current map. Right click baseline maize suitability raster and choose add to current map. If you are running the model, click the pause drawing button now, then click run. So pause drawing, and then we're going to run. Okay, let the tool start running. After the model finishes running, context pane, turn off the fusion maize suitability layer. Click the pause drawing button to resume the map display. You have created a prediction output for fusion maize suitability that can help agricultural ministers plan for future climate change and safeguard farmers and food security. Save your project. So in step 5, we are going to review model diagnostics. So it seems like we have almost finished running the tool. So let me pause while this thing runs. Okay. Alright, so the tool has finished running. So let's go to the instructions. After the model finished running, the context pane, turn off the fusion maize stability layer, click the pause drawing, and then save your project. Let's go ahead and do that. So what they call it, fusion maize. Trained features. Sorry. After the tool is running, context pane, turn off the fusion maize suitability layer. Okay. Where is it? Oh, trained features. Okay, no problem. Let's just expand the results and then let's add this to see. Add to current map. Let's quickly go to step 5. When you run a model using the presence only prediction marking tool, a series of charts and tables are generated that display the performance diagnostics of your model. It is important to review these performance diagnostics to get a sense of how accurately your model is able to predict. Okay, review model diagnostic. So in this step, you'll access 2 of these charts to review the performance diagnostics of your model. If you choose not to run the model, read through the following steps and use the graphics provided for partial response of continuous variables and classification results percentage to examine your model's performance diagnostics. At the bottom of the contents page, under standalone tables, open the partial response of continuous variable. So let's go. Where is it? Okay, continuous. Click on open. And then the partial response of continuous variables chart summarizes and visualizes the impact of each bioclimate variable on the probability of presence of maize. You can click individual charts to explore the effects of specific bioclimate variables in more details. Individual charts show the suitability ranges for each bioclimate variables. When considered together, suitable areas will be where multiple bioclimate variables overlap to produce overall suitable conditions for the presence of maize. In the curve table, click the baseline bioclimate 07 in the second row, 4th column. Okay, in the curve table, let's see what happens. So in the curve table, click baseline bioclimate 07. Okay, baseline bioclimate 07. Where is it? 01, 02, 3, 4. 4. Where is 07? If I don't see it, I'll need to expand this. Okay. So baseline bioclimate 01, 2, 3, 4, 5, 6. Is it this? This is 8. This is 7. Okay, I've clicked on it. Yeah, it is. Yeah. The baseline bioclimate variable 07 represents annual temperature range. The presence probability of maize will be low if the annual temperature range is too cold or too hot. The presence probability of maize increases quickly from 0 degrees centigrade to approximately 15 degrees centigrade. Slowly declines from approximately 15 degrees centigrade to 25 degrees centigrade, and then declines rapidly as normal mean temperature increases above 25 degrees centigrade to 30 degrees centigrade. These charts are helpful for identifying suitable and unsuitable bioclimates for maize based on a single variable. You will now review a second chart. The contents page under trained features, double click classification result percentage. Okay, let's close this. Contents pane under trained features. They say we should double click what? Classification results percentage. Where is classification results percentage? Yeah, so we should double click. Okay, we have done that. To open the chart, okay, but the classification result percentage chart compares the observed and predicted classifications. You can use this chart as a training assessment to check how your prediction model performs when recognizing presence. The prediction model's accuracy is measured as the percentage of presence points that were correctly classified by the model. Point to the presence correctly classified classification portion of the bar chart shown in blue and use the pop-up to answer the following questions. What percentage of the presence points was correctly classified? And click the following view result link to. Okay, now you can see it's here. Background classified as potential presence, background unchanged, presence correctly classified, presence misclassified. Guidance to get started, focus on the presence bar on the right. The larger the portion in blue, the more that presence points are being correctly identified. So it's still an appropriate model. Next, check the background bar on the left. The larger portion in green, the
The larger the portion in green, the more that potential presence locations are being discovered from background points. Okay, so they said again 72% of non-presence locations were correctly classified by the model. May see a slightly different percentage because the model uses random points. Okay, do you see it here? 70.87, right? Okay. Now point to the background unchanged classification of the bar chart shown in gray. Okay, we should do that. Let's do that. This one is 19.31. Say the background unchanged classification of the bar chart confirms that lack of presence was observed and that according to the prediction model, no presence should be observed in those areas. If the background unchanged gray classification and the presence correctly classified blue classification are the largest portion of your chart, then your prediction model is performing well. Close both charts and save your program. In this step, you switch charts to review the performance diagnostics of your model. Step 6: convert point features to raster. Okay. So close this. Where are we? I loaded these two from the results. Okay. Where are we? Are we in step 6? Okay. So reviewing the performance diagnostics for a model allows you to confirm that the model is performing as intended and that the results are valid for use. After reviewing the performance diagnostics for your Maize Suitability model, you have decided that the results are valid. Because the baseline and future Maize Suitability layers are both point features layers containing 5.2 million points, you want to convert them to raster layers, a format that will be easier to visualize and share. In this step, you will use the point to raster tool to convert both of the presence only prediction output layers from point features layers to rasters. The Geospatial will search for and open the point to raster conversion tool. Okay, so where is it in view? Click back, point to raster. Conversion tool, right? If you choose not to run the model and instead add the results to your map, read through the instructions in this step, but do not run the point to raster tool. You already have the final raster layers that you need to compare the results. In the next step, set or confirm the following parameters. Input features should be baseline Maize Suitability. Okay, so yeah, let me bring this in like so. This way you're supposed to be, right? Okay, page features baseline sorry, said input features should be baseline Maize Suitability. Okay, let's look for that. So input features baseline Maize Suitability. Value field probability of presence. So value field is probability of presence. Let me just remove these results layers that I added, these two, from the results geodatabase. Good. Output raster is baseline Maize Suitability underscore raster. Output underscore raster, so just my raster there. And then cell assignment type is equals to some priority field is equals to none, and then for cell size, click the browse button. Under project, double click folders, double click the Maize prediction modeling folder, then the GFSAD folder. Select GFSAD TIFF and click OK. GFSAD. Okay. Cell size. Browse folder, Maize prediction, GFSAD.stif. Good. Value fields indicate which field in the attribute table will be used to assign values to the point raster layer. Probability of presence classifies the probability of the presence of maize for each cell in the layer. Cell assignment type lets you choose the best method of determining how the cell value is assigned when more than one feature falls within the cell. For cell size, you use the GFSAD layer to indicate that the cell size for the new raster is 1 square kilometer. It may take a minute for the tool to run because of the number of points. Click run. You now convert the feature Maize layer, stability layer, into present for the input feature. Click down arrow, feature Maize stability. For output data sets, feature Maize stability raster, and then click run. Okay, it's step 7. We compare our results. So this is okay. Okay, so we'll run, and that's it. So it has finished running. So we are going to change this for the future Maize suitability, and also just change this baseline to future, like so. Good. Perfect. And now we'll run the tool. Okay, so the tool has finished running. So it said after the tool finishes running, the contents pane, turn off the trained features layer. Save your project. You have converted the baseline and future Maize stability layers from point features layers to raster layers to facilitate visualizing and sharing the results with the agricultural ministers in Africa. Step 7 is to compare the results, as review the model. Final step in the iterative workflow is to review the results of your prediction model. The goal of using a presence only prediction model is to compare the change between baseline and projected suitability. However, when you converted your prediction output layers from point features to raster layers in the previous step, the layers were added to your map using symbology that is difficult to interpret. In this step, you will update the color scheme of the symbology to make it easier to compare the results and visualize the change in maize suitability in Africa. In preparation, you first organize the layers in the contents pane. The contents pane, click and drag the future Maize suitability raster layer to the top of the drawing order. Click and drag baseline Maize suitability raster layer above the future Maize. Okay. So is future Maize. Okay, they're already in order. Okay, future Maize. Raster. So we can drag this one up. Then we'll drag this one above it. Up. Good. That's it. Good. Right click, go to symbology for color scheme, click the down arrow, check synonyms, and then scroll down to select the yellow green continuous color scheme. So yellow dash green. So let's do that. It's quite easier to just click on this to open the symbology pane. Click on the down arrow, show names, and then yellow to green. What is it? Yellow to green, right? So let's look for that. UVWXY. Yellow. yellow greens. Is it this one? No, that's not it. That's not it. That's not it. Yellow to green. Yellow to green. I don't see you. Let me pause this video and find you. Okay, I found it, right? And then I guess I'll do the same to the second one. Let me scroll down here. Look at it. Down, 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 down. Yellow to green continuous. This is it. Okay. Yellow areas on the map represents the baseline or current areas that are not suitable for growing maize. The green areas represent the areas that are suitable for growing maize, darkest green areas being the most suitable. To compare the baseline results with the future results, we will use the same symbology settings for the future maize stability raster, and I've already done that, right? Okay, open the symbology pane for the future maize raster. At the top of the click the pane display option button and choose import from layer. The apply symbology from layer to displays. Set or conform the following parameters: input layer, symbology layer, click run. Oh, let me just click on anything for this one and follow the steps so that I can learn something else also. It says in the symbology pane for the future maize suitability, at top right of the symbology pane, click the pane display options button and choose import from layer. Okay. This import from not layer file. Import from layer. The apply symbology from layer to display. Set or conform the following. Input layer is the future maize suitability raster. Is this? And then the symbology pane layer is the baseline. Okay. Click run. With both the baseline and future layers symbolized using the same color scheme, you can now use the swipe tool to visually compare changes stable maize locations in Africa. So basically, let's click on run. Sharp. Okay. Okay. First, you change the base map to one that contrasts more with the symbology colors. On the ribbon from the map tab in layers group, click base and choose imagery. Now you will activate the swipe tool. So we're going to change the base map to imagery. So map, base maps, and then imagery. Good. Let this thing load. Can turn off these other things too. Okay, so compare the baseline of future shows that for it says on the ribbon click the raster layer tab and content pane select the baseline maize. Okay, on the ribbon click the raster, and then this is for the swipe tool, so we click on this. Note that there are two, so click on this and then okay, click on raster and then we click on swipe. Jesus, did I make any mistake? Okay, so just to make sure that if I'm doing the right thing, I can go ahead and remove these two layers and just load them from the results layer and do this quickly. So just in case if we made any mistake in our analysis, let's just use the results layer. And now okay, that they provided. So this is the baseline maize suitability raster, the one on top, and the one below it is the future maize suitability raster. We could see it like so. Okay, so does it for this. Comparing the baseline, the future results shows that for the SSP3 7.0 climate scenario, stable land area for maize will shrink significantly by the mid-century period of 2041 to 2070. The loss of even smaller areas of cropland can put the food security of a country at risk. Prediction modeling allows forecasting and planning for such changes to minimize the impact of climate change, especially for vulnerable populations that depend on smallholder agriculture as their main source of income. Save your project. You have explored the results of your prediction model by comparing baseline and future suitability for growing maize in Africa. Exit ArcGIS Pro. In this exercise, you trained a prediction model using baseline bioclimate variables to identify current maize suitability in Africa. Then you used your trained model to create a prediction model for future maize suitability based on the SSP3 7.0 climate scenario for the mid-century period of 2041 to 2070 and compare the results. So here is the end of this exercise. Thanks for staying tuned. Bye.